So what we are doing at this point, our goal, for this part, we want to introduce a concept called a growth function concept. So why we need to use this concept? The top level goal is we want to characterize all the efficiency functions for all the algorithms. We want to define appropriate categories for all the efficiency functions. To do that, so but if we use efficiency functions directly, some less important details contained in the efficiency function, we don't want to include those less important details. So we want to take the most important part from the efficiency function. Then we use that main part to define categories. So that most important part inside efficiency functions, that's the growth function concept. Now we need to first, let's get a definition of growth function. Then let's look at how to define appropriate categories for all the efficiency functions. All right, so that's the roadmap, current roadmap. Now let's look at the growth function concept. How do we remove the less important details? What is the major term in the efficiency function? So we only want to keep the major term. We want to ignore the minor terms. All right. So here, we saw a concept called a dominant term before. When we learned the linear search topic, we saw this concept, dominant term. All right. So let me use a simple example to explain this dominant term. For the selection sort, we find the efficiency function. So this is the efficiency function. All right, I need to change the pen color. All right. All right. So this function, you can see, original efficiency function contains a lot of less important information. That's the distraction part. So we don't want to keep that part, less important, minor terms, less. So we want to remove that part. So let's remove it by two steps. The first step, we do expansion, so we get two terms. In these two terms, the first term is dominant. Dominant. So if you want to ask me, what do you mean dominant? So we will see that later. We will do some computation to show you the dominance, how dominant it is. All right. So first, we only keep the dominant term and throw away all the other terms. So that's the first step approximation. First step approximation. But dominant term still, it contains this coefficient, one half coefficient. And this constant coefficient, not as important, the impact, let's say in this way, the impact of this constant is not as big as the variable, right? Variable, your n, can increase, becomes larger and larger, but the constant never changes. So this constant part, less important than the variable part. So here we want to treat, when we do the characterization, remember our goal, doing characterization. So when we do the characterization, we want to define our category containing the critical part. Yeah. So this constant part is not that critical. So we want to put all the functions with the leading constant. Yeah. Any leading constant. We want to put them in the same category. Yeah. So that's our consideration. Okay? Yeah. So although your constant could be different, yeah, 1, 2, 3, different constant, but our main focus is at the variable part, not at the constant part. Yeah. At the variable part. Yeah. So for that reason, even if the constant part different, but we want to put those functions with the same variable part, but different constant part, we want to put them in the same category. Yeah. So with that in our mind, so when we do the simplification, the second round simplification, we want to skip the constant part. Okay? Yeah. After we skip the constant part, yeah. Yeah. After we remove 1/2 constant, n squared, that's our growth function. Yeah. So after this 2-round simplification, yeah, we get to the growth function. Yeah. As simple as possible. We want to make our growth function as simple as possible. Here, for this example, selection sort, the growth function for its efficiency function is n squared. Yeah. All right. Then I want to show you the dominant part. How dominant it is, the dominant term. Yeah. So here we take a calculation. Let's take the ratio of these two terms. The first term over second term. Take the ratio and then look at when n goes to infinity. We want to look at its limit. Yeah. So in calculus, we know how to calculate this limit. Yeah. Yeah. Because this calculation will tell us some important information. All right. So let's do simplification before we do calculation. Yeah. Then you take the limit of n when n goes to infinity. Then its limit is infinity. Yeah. Its limit is infinity. All right. Now, can you see how dominant it is? When you see this infinity, can you see the dominance, how dominant it is? The top term over the bottom term, the ratio is infinity when n goes to infinity. Yeah, yeah, because when you understand the dominant, yeah, you know, it's a vague term, right? Yes, it's a vague term. Yeah, but no matter how vague it is, when the ratio is infinity, so we are convinced that the first term dominates the second term, right? And no argument. Yeah. All right. So now we should feel comfortable throwing away the second term, right? Yeah. Yeah, but because the portion is so tiny, so tiny. When n goes to, yeah, here, n goes to, some of you may argue n goes to infinity because in the real world situation, n never goes to infinity, right? Yeah. Yeah. But actually, yeah, we only worry about the behavior when n is very large, right? Yeah. When n is not that large, then we don't have problem. Excuse me. Our current computing power can handle n not that large. Yeah. Yeah. But if your growth function grows too fast, probably our current computing resource cannot handle the computation. That's our main concern. So that's why we look at n goes to infinity. Extremely large. Yeah. All right. Yeah. So then, next. Yeah. All right. Now you have this, growth function concept. Yeah. All right. Next, we want to use the growth functions to define categories. Yeah. All the functions with the same growth function, we want to put them in the same category. Yeah. That's simple. Yeah. With same growth function, yeah, we put them in the same category. Yeah. All right. B.2, this time we want to compare growth functions. Yeah. All right. So let's go back to our element uniqueness problem. Yeah. In that one, we have two methods, right? Method 1 and method 2. Yeah. We haven't compared which one is better. Yeah. All right, so let's do it. So now we are ready to do the comparison. The first method, the worst case growth function, efficiency function first. Yeah. Efficiency function first. All right, yeah. The second method, efficiency function. Yeah. So now let's do the comparison. Before we do the comparison, let's extract growth functions from these two efficiency functions. Extract. All right. For the first first efficiency function, after extraction, we have this n squared growth function. For the second efficiency function, the dominant term, yeah. So we have this n log n growth function. Yeah. The simplest form we can get. Now we are ready to do the comparison. Still, we take the ratio and we calculate the limit. Yeah. All right? Yeah. Let's take the limit. Okay? Yeah. After simplification, we need to calculate the limit of n over log of n when n goes to infinity. Yeah. So this log function, actually the base is not that. Yeah. Here I didn't put the base, yeah, because we can use the general base. Yeah. The base number, the specific base number is not that important. Yeah. Here, what I need is only one condition on the space. Yeah. So I use some positive, positive number a, and I also want this a, base a is greater than 1. Yeah. A should be greater than 1. Yeah. Yeah. Otherwise, yeah, something is wrong. Okay? Yeah. For example, when n equals 1, the log function becomes 0. Yeah. So we cannot use that. Yeah. When n less than 1, greater than 0, the log function is a negative value. So that's not our growth function. Our growth function should be a positive function. Yeah. So it's reasonable, yeah, we choose a positive number greater than 1 as the base. All right. When we do the comparison, the numerator is n, denominator is log function, and how do we know? How do we calculate the limit? Yeah. So there is some method we can use. Yeah. Here, yeah, I just give you the answer. The limit is infinity. When n goes to infinity, limit is infinity. Yeah. How to see it? Yeah. So how do you see it? Yeah. Yeah. So there is some way we can see it. Yeah. All right. The first way to see it, yeah, so we do some variable substitution. Yeah, variable substitution, yeah, because log function, for many people, they feel it's not easy to see the trend, the behavior of the log function. Yeah. So we try to eliminate log function. So let us introduce a new variable u that equals this log base a of n function. Yeah. Then, by the definition of log function, n equals a to the u, exponential function. Yeah. So after this variable substitution, you can see our original ratio becomes, under the new variable, u also goes to infinity. Yeah, because when n goes to infinity, u also goes to infinity. So we have exponential function a to the u over u. Yeah. How to see this ratio is infinity? Yeah. Still not that easy, right? Yeah. Still, it may not be that easy. But yeah, in our real world experience, people have this kind of, understanding. So that is, the exponential function grows much faster than polynomial function. The denominator is a special polynomial function. So exponential function always grows much faster than the polynomial function. Yeah. So that's the, people always say in that way. Yeah. All right. It dominates any polynomial. Yeah. We can prove it. Yeah. Later we will prove it. Yeah. But that fact, yeah. So many people say they use this fact all the time. Yeah. Exponential growth. Yeah. When you talk about exponential growth, it's always very fast. Yeah. All right. Yeah. Next, we want to use some special math tool, L'Hopital's rule, to do the limit calculation. So when we calculate the limit, so you can see, if we use the direct way to do the calculation, that's not very convenient. Yeah. So a lot of things we cannot control. Yeah. Because the numerator goes to infinity, denominator also goes to infinity. How do we compare infinity over infinity, right? Yeah. So the hard part is how to compare infinity over infinity. Yeah. So L'Hopital's rule provides a powerful tool to help us, to allow us to find the answer in this situation. So let me talk about this L'Hopital's rule. All right. Use L'Hopital's rule to calculate the limits. Yeah. First, I need to explain this L'Hopital's rule. When you calculate the ratio of two functions, all right. So when you have the situation, our current situation, so the L'Hopital's rule basically tells you the limit of two functions equals the limit of the ratio of two derivatives of those two functions. Derivatives. Yeah. But here, in order to apply the L'Hopital's rule, there is a condition. So you need to be very careful. Yeah. First, you need to look at the condition first. Yeah, special condition first. Yeah. So that condition is the ratio of the two functions must be called indeterminate form. So what's that indeterminate form? Yeah. Infinity over infinity. This form is indeterminate, yeah, because it could be everything. Yeah. Infinity over infinity could be infinity, possible, yeah, because think about if you look at the n squared over n, this could be infinity, right? The ratio. Yeah, yeah. So it could be infinity. Yeah. And it could be 0. Well, because you look at the n over n squared, right? Yeah. The limit is 0. Yeah. And it could be constant, right? Yeah. So let's say n squared over 3n squared plus 1, right? So it could be a constant, 1/3, yeah, and so on. Yeah. So that's why we call it indeterminate form. Yeah. Okay. Yeah. All right. And there are other indeterminate forms. Yeah. For example, 0 over 0, indeterminate form. Yeah. Could be anything. Yeah. All right. And some other indeterminate form. For example, 1 to the 0. How about that? Yeah. 1 to the 0. Yeah. So although you feel, yeah, this is determinator, right? Sorry, 1 to the infinity, not 0. Yeah. 1 to the infinity. How about that? Right? 1 to the infinity, yeah, indeterminate. Yeah. Could be anything. Yeah. Could be anything. Yeah. All right. Yeah. And there are many other indeterminate forms. For example, infinity minus infinity, right? Yeah. Infinity minus infinity. Could be anything, right? Yeah. All right. But for this class, yeah, we only work on the first determinate form. Because our growth functions always grow to infinity. Always grow to infinity. Yeah. So we have this infinity over infinity growth function, indeterminate form. All right. Then let's take the ratio. Yeah. Ratio of the two functions. Yeah. All right. Yeah. Yeah. So now let's look at this limit. Yeah. First, infinity over infinity, no problem, right? Yeah. So you need to check it. Infinity over infinity. Then we can apply this L'Hopital's rule. L'Hopital's rule tells us, because if we calculate limit directly too hard, let's calculate the derivatives of each function in the ratio. Yeah. All right. What's the derivative of exponential function? We have a formula. Natural log of a, constant part, times original exponential function. Derivative of u, that's 1. Yeah. Now you take the ratio, constant 1, constant, but this exponential function still goes to infinity, right? So constant times infinity, so your answer is infinity. Then the original ratio goes to infinity. Yeah. So here you can see, how do we get the exponential function dominates one monomial here? This u is a linear function. Yeah, people call it linear function. Yeah. All right. All right. Yeah. So you see the power of L'Hopital's rule in this first example. Yeah. All right. Then next we need to be, because when we apply the calculus tool, we should be a little careful on the, because we want our calculation rigorous. So we don't want to leave some big hole in our calculation. And here in this calculation, actually, there is some potential problem we need to consider. So that is the variable type, right? Yeah. So here, because we need to take derivatives on two growth functions. how do you know derivatives exist, right? Yeah. How do you know the derivative exists for those two growth functions? Yeah. So here we need to make sure the derivatives must exist. Yeah. So for that reason, we need to consider continuous variable, not discrete variable. Not discrete variable. So there is a difference between continuous variable and a discrete variable. Yeah. So what's the difference? All right. The difference is, let's look at this version. N over log of n. N can only take discrete values, right? 1, 2, 3. Yeah. So here, the values for n, discrete values. So we call this n discrete variable. It's not continuous variable. All right. Discrete variable, so then there is a problem. When you look at its derivative, how do you define derivative? The definition of derivative, it does not exist. For for a function with discrete variable, its derivative does not exist. Yeah. All right? Yeah. So, but we don't want to throw away the powerful tool of L'Hopital's rule. Yeah. Yeah. If for the reason, this discrete variable reason, you cannot apply L'Hopital's rule, yeah, then it's not good. Yeah. Yeah. So then we want to find a way to get around this discrete variable. Yeah. Now we can make it happen. Get around discrete variable. Yeah. How to get around? Yeah. Yeah. We consider a continuous version of the discrete version. Yeah. Can we look at the continuous version? In this version, we use x as the variable, but the x takes continuous values, not discrete values. All right? And when we look at the continuous version, we can apply L'Hopital's rule. Yeah? Because the derivatives exist. Yeah. Now you have no problem. For that one, if you apply L'Hopital's rule, people can argue the derivatives do not exist. Yeah. Here, no problem. We can apply L'Hopital's rule because it's so powerful. But still, we want to use it. All right. After we apply L'Hopital's rule, numerator, derivative 1, denominator, we can find the formula. We assume base A, so that's 1 over denominator of this, a derivative function, log of A constant times variable x. After simplification, so constant times positive constant. Now this is a positive constant, A greater than 1. Yeah. Positive constant times x. X goes to infinity, so then it is infinity. All right. So here you can see, after we switch it, the ratio, same ratio, but the only difference that we change from discrete variable to continuous variable. Yeah. So we can apply L'Hopital's rule, we get the result. Yeah. After we get this answer, infinity answer, we need to go back to the original ratio. Yeah. How do we go back? That's the question. Yeah. Because the variable types are different, right? The variable types, one discrete, one continuous, they're different. How can we use the answer? This is the answer for the continuous version to say the discrete version also has the same answer. How can we say that? Right? Yeah. 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 By the definition of the limit. Yeah. So limit in calculus. So there is a definition. Yeah. So based on the definition of the limit in calculus, we can say the limit of this original ratio with discrete variable is also equals to the infinity. Yeah, why? Yeah. Let me explain. Why? Based on the definition, we can make that conclusion. Yeah. All right. So let's recall the definition a little bit. Yeah. So here we do not need to, repeat the whole definition, but I only want to talk about one special point here. Now look at it when n goes to infinity. Yeah. This arrow sign, when n approaches infinity, does it tell us in which way approaches to infinity? Yeah. Because when x goes to infinity, there are so many different ways to go infinity, right? Yeah. Infinity is the destination, but you have many different paths get to the same destination, right? Yeah. Here I give you a few examples to infinity. Yeah, because so many different ways to go to infinity. One way, how about I take x as a sequence, 1 square, 2 square, 3 square, n square. Yeah. That's one way to infinity, right? Yeah. How about that? Yeah. Another way, 1 root of 2, root of 3, and so on. Root of n. It can also go to infinity, right? Yeah. There are so many different ways to go to infinity. Which way do you mean here, right? Yeah. When you write this way, you do not specify which way. Okay? Yeah. Then it means any way is okay. Yeah. It doesn't matter which way you use. Which sequence you use it to approach to infinity, if only it goes to infinity. Yeah. It's good enough. Yeah. It's good enough. All right. Based on that understanding, now, how about we choose the special sequence, 1, 2, 3. The consecutive integers, we choose this sequence. It's also okay, right? Yeah. We choose this sequence when we look at the limit, infinity. It's also correct, right? Yeah, also correct. Yeah, based on the definition of limit, it's also correct. But when we choose the consecutive integers, that's exactly our discrete version of the limit. Yeah? Yeah. So we can apply it. Yeah. Same answer, yeah, limit, yeah. Infinity answer. Yeah. All right. Yeah. So here, I spent quite some time to explain the difference of these two ways. Yeah. Because it's very easy to make a mistake. So if you apply limits on the discrete functions directly, yeah, so many people do it in that way. Yeah. Actually, our textbook do it in that way. Our textbook apply limit on discrete functions directly. Yeah. Yeah. So you should be very careful. Yeah. All right. Then we move to the next topic. Yeah. All right. Yeah. All right. So here, now the conclusion. Yeah. Because after we get this, we can get a conclusion. Yeah. Our first method is much slower than the second method. Yeah. 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 All right. And the second method, n log n, yeah, second method, growth function second method, is much faster than the growth function of first method. Yeah, so that's our conclusion. Yeah, all right. Yeah. All right, next, B.3, bubble sort. Yeah. All right, so let's study our second sort. Yeah. The first sort, selection sort. Second sort, bubble sort. All right. Yeah. All right, yeah. So this time, yeah, we understand the same old sort problem, but we use a different view to understand. Okay, yeah, this time we look at the same problem with a different view and see if we can get a different solution. All right, yeah. Here I use this diagram to show you the relationships among the elements. We need to study some special property. We want to find some property here. Yeah. All right. Yeah. This time, yeah, we want to do comparison. Yeah. Let's do, yeah, because when we saw this array, we need to do comparisons. But when we do comparisons, what information do we get? Yeah. Here, I want to look at the one special pair. Yeah, let's do comparison. Compare these two elements. All right. When we sort this array, we want all the elements in ascending order. Okay? Ascending order. So if the elements follow that ascending order, yeah, so that's our desired property, right? That's the desired property. Yeah. But you need to consider, yeah, some of the elements may not follow that property. Yeah. Some of the elements may not have the ascending order. Yeah. Here, let's look at one special pair of elements. Within that pair of elements, they are out of order. Yeah, so that property, we feel, yeah, so based on our understanding, we feel it is related to the solution. Yeah. Out of order property related to the solution. Okay, all right. So let's do observation for critical property, yeah, based on the order information. Yeah. If the array is not sorted, yeah, not sorted, not in ascending order, yeah, what conclusion can we get? There must be two adjacent elements that are out of order. Yeah. Can you see this property? Can you see? There must be two adjacent elements that are out of order. Okay? Yeah. So first we need to understand if this statement is correct or not. Two adjacent elements out of order. Okay? Yeah. All right. Some of you may feel not easy to see it, right? Some of you may feel, yeah, it's a little hard to see it. Yeah, two adjacent elements out of order. Okay, yeah, yeah, all right, yeah. So let's try to understand this statement first. Okay, yeah, this property first. All right, yeah. To understand that, yeah, I want to introduce a new concept called inversion concept. Inversion concept. Okay, all right. So what's the inversion? Yeah. Here when we study a pair of elements, yeah, we want to look at if in this pair of elements they are in order or not in order. That's the question. In order or not in order. Okay? All right. So we define this inversion concept for the case that this pair of elements is not in order. So not in order, it means when the subscript's in order, I less than j, that means subscript in order. Okay? Yeah. I subscript is smaller than j subscript. So when the subscript in order, but the element values are not in order, a sub I is greater than a sub j. Yeah. So when this phenomenon happens, we get an inversion. Because with one inversion is enough to make the whole array unordered, right? Yeah, the whole array unordered. If the whole array has one inversion, then it's unordered. Yeah. So you can see the importance of inversions. Yeah. All right. So with this new concept, now we want to use this inversion to help us understand the order property of an array. All right. Yeah, let's look at another statement. If the array is not sorted, then there must be one inversion, right? At least one inversion, yeah? That's easy to see, right? Yeah. Because if there is no inversion, when you select any two elements, the later one is always greater than the former one, right? Yeah. If that occurs, that property is there, then we can say all the elements are in order. Yeah. So this statement much easier to understand than the previous statement, right? Yeah. So if an array is not sorted, there must be an inversion. Yeah. All right. Then now we want to move from this statement, the second statement, to first statement. Yeah. Because the first statement is stronger than the second statement. Yeah. Look, compare the difference between these two statements. The second statement is stronger than the first. Why stronger? All right. The first statement, there must be two adjacent elements out of order. Does it mean inversion? Yeah. The first statement tells us there must be an adjacent inversion. Yeah. The second statement, yeah, it does not say adjacent, right? Yeah. This means this inversion is a global inversion. Okay? All right. So the second statement, much easier to see, because if there is a global inversion, then the whole array is not sorted. Yeah. It's easy to see. Yeah. But the first statement is stronger. Yeah. It reduces, yeah, because the global inversion, yeah, you know, could be the pair you select everywhere. Yeah. But this time we restrict ourselves. We don't want to select global inversions. We restrict ourselves to only adjacent inversions. Adjacent inversions. Yeah. All right. So you can see we make our statement much stronger. Yeah. Yeah. All right. So there is a gap, right? So we want to bridge the gap between global inversions and adjacent inversions. Yeah. All right. But that gap can be bridged easily. Yeah. Not too hard. Yeah. All right. So our next statement, we bridge the gap. Yeah. if this global version is correct, yeah, we know now, we agree it's correct. We can see it easily. Yeah. So then from that statement, we can derive this adjacent version easily. Yeah. Why? Yeah. Think about. Yeah. You can imagine. Yeah. So here, you can imagine. Yeah. Yeah. One way to see it. Yeah. People use the contrapositive method. Yeah. Contrapositive. Yeah. Method. Yeah. All right. There must be an adjacent inversion. Think about if there is no adjacent inversion, what will you get? Yeah, contrapositive, you negate the conclusion part. Yeah. So what's the contrapositive method? In your discrete math. Yeah. So you study this method. So we negate the conclusion, and then we will get a contradiction to the hypothesis. All right. Yeah. So think about if no adjacent if no adjacent inversion, what can you get? Okay? All right. When you select any two adjacent elements, they are in order. Okay? They are in order. All right. So let's start from the first pair. First pair in order. Second pair in order. Yeah. We keep going up, right? Yeah. Keep going up. Then, from first to last, you get ascending order. Yeah. So that's simple. Yeah. When you negate the conclusion, yeah. So we negate conclusion. No adjacent inversion. Yeah. We keep going up. Yeah. Yeah. So we scan from the first element to the last element. Yeah. Every pair, every adjacent pair, when we do comparison, yeah, not inversion. Yeah. Second one always greater or equal to the first one, always greater or equal to the, always. Yeah. We have this property. Then, when you reach the end, you get ascending order array. So simple, right? Yeah. So that's we can see this stronger version of the statement. Yeah. Now, based on this stronger version of this critical property, we design our algorithm. Yeah. So our algorithm based on this stronger version. Yeah. So we can save a lot of work. If you do the, weak version, this is a weak version. Okay? And you need to do comparison. You need to do global comparisons, right? Yeah. You need to do global comparisons. Yeah. But here, yeah, we only need to do the, local comparison, adjacent comparison. We do not need to do global comparison. Okay? All right. Yeah. Next, we will solve this problem. We need to sort. All right. Yeah. So let's do the implementation. Yeah, sort. Yeah. Sort it. All right. Yeah. So now, when we do the sorting, actually, think about the work we are going to do. We want to reduce the number of inversions, right? Yeah. So when you do your work, so our main idea here, so the main idea reduce the number of inversions. Okay. Yeah. So your algorithm keeps reducing the number of inversions. If you can reduce the number to 0, you get it sorted. Yeah? Yeah, because our goal, we want to, yeah. So we count the number of inversions in this array. Yeah. We keep reducing. Yeah. Yeah. When we get to 0 number, yeah, it's automatically sorted. Yeah. So that idea. Yeah. All right. The question is, how do you reduce the number of inversions? Right? How do you reduce number of inversions? Yeah. Actually, yeah, it's very simple. Yeah. Let's look at just the one inversion. Yeah. Every time we look at the one inversion, the current inversion, when we encounter the current inversion, what should we do to remove it? Yeah. So we detect one inversion. We want to remove it. Yeah. Swap. We just swap those two elements. Then inversion is gone. Okay? Inversion is gone. Yeah. All right. So now the algorithm becomes, yeah, these two main steps. Yeah, becomes, yeah, detection, inversion detection plus swap operation. Okay? Inversion detection. Yeah. You do comparison. When you do comparison, you can see if it is an inversion or not, right? Then, when you find an inversion, you just swap the elements of that inversion. Then that inversion disappears. That inversion disappears. Okay? Yeah? That's simple. All right. Yeah. So based on that understanding, now we are ready to write our implementation of the algorithm. All right. In our implementation, so the idea, remove all the local inversions by local swaps. Because based on our stronger statement, we only need to remove adjacent inversions, right? Yeah. All right. Yeah. Swaps. Yeah. All right. So, yeah. So let's look at step 1. We start from the first element for each scan from the very beginning. Yeah. To the end. Yeah. So we need to look at the end, appropriate end here. The starting point always the same. The beginning of the array, the starting point, the same. But the end point could be different. Yeah, the end point could be different. All right. That's the first step. Yeah. Second step, do swaps one by one from left to right when necessary. Yeah, because sometimes you do not need to do swap, right? Sometimes you do not have inversion, then you just move on, right? Yeah. So here, this swap step, only if necessary. Yeah. Yeah. Only when it is necessary, we do swap. Otherwise, we do the next inversion detection, and so on. All right. Then the third step, each scan, we need to stop at the first in-place element. Yeah, because every time, yeah, think about, so there is another important property we need to observe. All right. After first scan, let's look at the first scan. After the first scan, where is the maximum? The maximum element in this array. Yeah. After the first scan, where is the maximum? Okay? Yeah. Because assume the maximum's original location is somewhere in the middle of the array. Yeah? But when you do local swap, when you do adjacent swap, you always push the maximum to the end, right? Yeah. You keep pushing maximum toward the end. Yeah. Yeah. And when you reach the end, the maximum must be at the end, right? Yeah. So after the first scan, the maximum, the max is in place. Yeah. The max is in place. Yeah. The first scan, max is in place. Yeah. All right. Yeah. Keep pushing. Yeah. No matter what location it has, we keep pushing the max to the end. Yeah. When we reach the end, yeah, the max is at its right place, so in place. All right. That's the first scan. The second scan, then we keep pushing the second maximum, right? Second largest element. Yeah. Yeah. And push it to the end. Yeah. But the second round, we do not look at the maximum, right? Yeah. Because the maximum already in place. So we can eliminate maximum from the consideration. Yeah. So the second round scanning, yeah, we keep pushing the second largest element to the current end. Yeah. To the current end. Yeah. So then we keep doing that. Okay? Yeah. Every time we put the current largest element at the end, to the end. Yeah. We'll put. So then eventually we will put all the elements in place. That's the idea. Yeah. All right. So this algorithm, yeah. So let's summarize it. Okay. So there is one element in place for each scan, at least one element. Yeah. Because you keep pushing the largest element. Currently, the largest element in place. All right. The in-place element of each scan appears at the end of the current array. Now, that's property. The current array is a subarray that excludes all the in-place elements. Yeah. All right. Yeah. So that's the whole picture. Yeah. After we understand this, our second sort algorithm, that's the whole picture. Yeah. All right. Visual imagination. Yeah. All right. So now, you can see this is a completely new algorithm. Yeah. The swab looks like a bubble moving to the right. Yeah. So that's why people call it bubble sort. Yeah. So, yeah. Well known. Yeah. Yeah. But here we use inversion to understand this bubble sort. Yeah. All right. Yeah. Yeah. Efficiency. Yeah. So we can do efficiency analysis. Yeah. But pretty much the same as the selection, that of the selection sort. Yeah. The first round scan, the number of comparisons, yeah, because the first round scan, number of comparisons, n minus 1, right? Yeah, first one. The second round scan, n minus 2, and so on. The last round, 1, okay? Yeah. So you get a 1/2 n times n minus 1. Yeah. Yeah. Similar analysis of the selection sort. And this efficiency function is the same for all the cases. Best case, worst case, average case. Yeah. That's also the same as the selection sort. Yeah. Yeah. The same property, yeah, of the that selection sort. All right. Yeah. 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 And in this algorithm, what's the basic operation? Yeah, because this algorithm, we use two operations, comparison and a swap. Yeah. Which one is more basic? Yeah. Comparison operation more basic or swap more basic? Yeah. Yeah. The answer is comparison more basic. Because if you do not have inversion, you do not need to do swap. No swap. But you still need to do comparison, right? Yeah. So you have more chances to do comparison, but you do not have that many chances to do the swap operations. Yeah. For example, for ascending order, yeah, you can consider an extremal case. Extremal case, so you consider ordered array. For an ordered array, how many comparisons do you need to do? Yeah. Same number of comparisons. But how many swap you need to do? Ordered, 0 swap. Because no inversion, so no swap. Okay? Even if no swap operation, you need to do the same number of comparisons. Yeah. But in our textbook, there is a improved version of this bubble sort. Improved version. Yeah. Yeah, because that is each scan, at the end of scan, you need to count the number of swaps. You need to use a new variable, counter variable. Yeah. Okay. Add a counter variable. Okay? Yeah. For each scan, okay? For each scan, you need to, each scan. This counter variable, every time when you detect inversion and you do a swap, you need to increment this counter variable by 1. Increment it, okay? Increment, plus 1, okay? So at the end, you need to check if this counter, this counter, let me use CNT, okay? If this CNT equals 0, then you stop. Yeah. Equals 0, that means no swap, right? Yeah. So at the end you check, not in the middle, okay? At the end of each scan, you check this counter variable, okay? If equals 0, already sorted. The whole array already sorted because no swap needed, right? For the whole scan from beginning to end, no swap needed. It means all the elements are already in ascending order. Why you still keep doing, right? Yeah. So that's the modified version of this bubble sort. Yeah. All right. So in that way, you can do better than this. This is the original bubble sort. Yeah. Original bubble sort. Yeah. All right. Cool. Yeah. That's the end of the part B. Yeah. So now we switch to part C. Yeah. The title, asymptotic notation. Yeah. So that's the hard part. Yeah. Because this concept is very abstract. Yeah. So we need to try our best to understand this concept. Yeah. C.1, Introduction to Asymptotic Notations. All right. Limits of two growth functions. So let's go back to the limit of the ratio of two growth functions. All right. Yeah. Yeah. So here, we consider all the possible cases when we take the limit of two growth functions. Yeah. All the possible cases. So there are 4 different cases we need to consider. Yeah. The first case, the limit is 0. Okay? The second case, the limit is positive constant. So this C, yeah, for our situation, the C cannot be 0. Okay? Yeah. Strictly greater than 0. All right? Then, third case, infinity. And then there is a fourth case. Fourth case, none of the three above. The fourth case. Yeah. We also need to study. Yeah. All right. Now, for these four cases, we want to get conclusions. Yeah? Because when we compare two growth functions, we want to get conclusions. Which one increases faster? Which one increases slower? Yeah. All right. Let's look at the first case. The limit of the ratio is 0. By our intuition, the g function increases faster than f function, right? Yeah. And here we use another concept in this situation. We use a concept called order of growth. Yeah, concept. Yeah. We use order of growth concept for this function. We compare the order, yeah, because that's those two numbers. So what's the order of growth of two functions? Yeah. At this point, let me give you a rough description, order of growth, yeah, of the concept. Yeah. All right. So that is, yeah, here I show you example. Okay, all right. So example. Let's look at a monomial. Okay, monomial. Yeah. And, yeah, so our variable is m. N to the k, yeah, k, some constant. Yeah. Then its order of growth is this k. Okay? That's simple. Order of growth, yeah, yeah, is k, right? Yeah. All right. So based on this initial understanding, I said this is a rough description, yeah, because some of the cases, this definition, this description cannot cover. Yeah, there are some cases this description cannot cover. So we will talk about that later. Okay, cannot cover. All right. But for this simple monomial case, our power function, yeah, power function monomial, yeah, that's simple, order of growth. So the order of growth of f function is less than order of growth of g function. Yeah. So that's for the case 1. Yeah. Case 2, yeah. Case 2, constant. The ratio is a positive constant. Now, case 2, we say they have the same order of growth. Yeah. Because when we look at the order of growth, the leading constant doesn't matter. We don't look at the leading constant. We only look at the exponent number. Yeah. So for that reason, for this case number 2, these two functions have the same order of growth. Yeah. Then case 3, the order of growth of f function is greater than order of growth of g function. Okay, yeah. All right. Then, yeah, yeah. Case 4, yeah. Case 4, because, yeah, the limit does not exist. Yeah. The other, yeah, because the limit does not exist. Yeah. 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 When the limit does not exist, yeah, we cannot make our conclusion. Yeah. We do not have any conclusion. Yeah. Yeah. But that means this limit method doesn't work. Yeah. 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 Here, the first two cases rely on the limit method. But the limit method sometimes does not work. Yeah. If the limit method does not work, when we need to find a different method to make it work. Yeah. That means this technique has a limitation. This technique has limitation. So we need to use a different technique to tell us which one grows faster, which one grows slower. Yeah. All right. Yeah. So that different method. Yeah. All right. So we need to. Oh yeah. Yeah. Before that. Yeah. So we need to. Yeah. Because when you use the representation, order of growth, write the statements like that, it's not very concise, right? So we want to use some concise notation to represent the meaning of those cases. Yeah. For that reason, we introduced the asymptotic notation. Yeah. The first asymptotic notation, little o notation. Yeah. So when the order of growth of f function less than order of growth of g function, or when the limit of the ratio f of n over g of n equals 0, then we use this notation. F function belongs to little o of g function. Yeah. So very simple, yeah. Very concise, yeah, but we know its meaning. Yeah. We do not need to use a lot of words to describe it. Yeah. We just use this notation. Yeah. All right. The second case, we use another asymptotic notation. Yeah, so big theta. Big theta asymptotic notation. Yeah. So we say f function belongs to big theta of g function. Yeah. The third case, another asymptotic omega, little omega. Yeah. Yeah, this is little omega. Because later we will have big O, we will have big omega. Asymptotic notation. So this one, little omega, it's meaning the limit of f function over g function is infinity. Yeah. All right. So that's the three asymptotic notations. Yeah. Three asymptotic notations. All right. Then we need to look at case number 4. Yeah. We need to find a way to answer, to give us the conclusion for case number. Oh, let me stop right here. Yeah, we need to take a 10-minute break.